Okay, good day class. In this video, we will talk about bulk modulus of elasticity, symbol EV. So ano ba tong bulk modulus of elasticity? Uh, it is a property that relates changes in pressure to change in volume. So for example, pag nagbago yung pressure, it either expands or contracts. So pag tumaas yung pressure, it will contract. Pag bumaba yung pressure, it will expand. So we have this formula, EV is equal to, we denote S as negative since it is inversely proportional to the pressure. So EV is equal to negative change in pressure divided by fractional change in volume. So kaya siya tinawag na fractional change because it is the percentage volume or change in volume divided by the original volume. So here, dV is the differential volume change. V is the volume of fluid. So we have here example of water. We have 2.2 gigapascal bulk modulus of elasticity. So we can relate the fractional change in volume to the change in material density. We have here mass is equal to density times volume. So dito tayo magsisimula to relate the fractional change in volume to change in material density. So let's differentiate both sides. So note that mass is constant. So differential uh, of mass is 0. So dm is equal to, so rho is variable. So we need to treat this as, we can differentiate this. So also the volume. So from differential calculus, we have here product. So UdV plus VdU. So rho dV plus V d rho is equal to 0. Okay, restructuring the equation above, we get rho dV plus V d rho is equal to 0. We need to transfer this rho dV to the right hand side of the equation. We get V d rho is equal to negative of rho dV. So now we need to combine the expression with same variable. So itong rho ibaba natin, then yung volume lipat sa kabila. So we have fractional change in density is equal to the negative fractional change in volume. So we have d rho over rho is equal to negative dv over v. So using that relationship that we derived a while ago, we can modify the formula. So, di ba, bulk modulus of elasticity is equal to negative of differential pressure divided by fractional change in volume. So, ito pwede natin itong palitan ng fractional change in material density. Yan. So, dahil negative ito, negative times negative, magiging positive na siya. Finally, we have bulk modulus of elasticity is equal to density multiplied by differential pressure divided by differential density. So here, the elasticity of an ideal gas is proportional to the pressure. According to the ideal gas law, for an isothermal constant temperature process. So, constant temperature. So, yung temperature hindi siya magbabago. Yung magbabago lang dito is yung pressure. Itong gas constant, yan, constant din yan. So, let's differentiate this again. So, using differentiation with R and T constant, we get D rho is equal to differential pressure divided by RT. So, let's restructure the equation. We get differential pressure over differential density is equal to RT. Yan. So, ito, magagamit natin to simplify the formula of bulk modulus of elasticity. Yan, substitute natin yung equation kanina. So, we have, di ba, ito yung original. Ito yung na-derive natin kanina. Bulk modulus of elasticity is equal to density times dp over d rho. So, we need to substitute this by RT. Magiging rho RT. Or simply, this rho RT is equal to the pressure of the gas. And this is for constant temperature process. So we also have adiabatic process, meaning no transfer of heat. So lalagyan lang natin to ng K, which is the ratio of the specific heats. So for constant temperature, EV is equal to P. For adiabatic process or no heat exchange, EV is equal to Kp, where K is equal to Cp over Cv. Okay, so let's practice. So I got problem 2.45. A pressure of 2 times 10 raised to 6 Pascal is applied to a mass of water that initially filled a 2000 cubic centimeter volume. So let's estimate its volume after the pressure is applied. And so yung fluid natin is water. We know that the bulk modulus of elasticity of water is 2.2 gigapascal. So giga means 9 zeros. So let's find for the differential volume. And finally the final volume, V2. So ito yung given. Initial pressure is 2 times 10 raised to 6 Pascal. Initial volume, let's denote that as V1 is equal to V. Is equal to 2000 cubic centimeter. Okay, so we have this formula relating the bulk modulus of elasticity with pressure and volume. Okay, so we need to find the differential volume. So let's isolate that. We get negative VdP over EV. So substituting all values, we get negative of 2000 cubic centimeter multiplied by 2 times 10 raised to 6 Pascal divided by 2.2 gigapascal. Now we get the differential volume, which is negative 1.818 cubic centimeter. Okay, so as you can see, since we increased the pressure, the volume decreased. So it contract, proving that it is inversely proportional to the volume. Now, to find the final volume, we get V2 is equal to V1 plus differential volume. So we have V1 originally 2000 cubic centimeter. So we need to add the change in volume. So yun yung use ng negative sign. So lagi ka lang add and always use the sign convention. So plus negative 1.818. And finally, we have final volume of 1998.182 cubic centimeter. Okay, so the volume was reduced.